right, we're talking about TEM still, so this is the second lecture on the subject of transmission electron microscopy. And I kind of wanted to show this micrograph from this article down here, and this is a really cool micrograph. And I have another one very similar that I found on social media that I'll share with you later in this lecture as well. But this is dislocation arrays, and they look like kind of the idealized I guess depiction of grain structure, because the dislocations, when they arrange themselves in a low energy state, low energy fashion as well, so you get this honeycomb type structure. I'm thinking this is two grains because I haven't looked at this article in a long time, so I've kind of forgotten, but this is kind of a double diffraction pattern here. And so we're seeing a diffraction pattern, I believe, from this grain and this grain. There's also some faults somewhere in there with kind of these doublet. And so very interesting. Have a look at this article if you want to learn more about it, but very beautiful, very nice imaging. Again, combining real space and reciprocal space to kind of figure out what's going on. I'm not doing a very good job interpreting this other than showing you that there's these really cool dislocation cells, this kind of array of dislocations that are kind of showing up, and a really cool honeycomb structure. If again, just kind of reminding you all what the TEM kind of looks like, it's basically just a big projector. A TEM specimen can almost be thought of as a slide, like for a slide projector, and the specimen goes in here in this little purple thing for the sample holder. The beam shines through it and then projects down onto a phosphorescent screen. Some systems go straight to a digital imaging system. The one we have in metallurgy goes to the phosphorescent screen. When you want to take a digital image, the phosphorescent screen moves up and then it hits a CCD. And so it's pretty much a projector. You have your transmitted beam and your diffracted beam. What we're going to talk about a lot today, and it's going to be kind of a short lecture, is sources of contrast. So it's kind of three main sources of contrast we're going to talk about. Mass thickness, so it's pretty a simple source of contrast. The thicker the sample, the less electrons can pass through it. Sometimes you also get this fringing effect, and that actually allows you to calculate the thickness of the specimen, so we'll see an example of that. Diffraction / lattice defect. If you read the book, it goes into a pretty decent solid state discussion. I'm going to insert kind of an older lecture on electron diffraction, and you get another variant of Bragg's law when you do that. And so there's kind of three flavors of Bragg's law that we talk about in this class. So the first one's obviously lambda equals 2d sine theta. We're going to see a second flavor of Bragg's law, and then we'll see kind of a third flavor of Bragg's law as well. And then bend contours. If your specimen is bent, you'll get contours, streaky lines on your micrograph as well. So kind of three main sources of contrast we're going to talk about today. Mass thickness, and so I don't know why I bothered putting an animation here. I'm sorry. All right, kind of did some magical editing, but mass thickness, so this part here where the grain is thicker than the light part, so more electrons are blasting through the specimen here on the lighter part. And let me laser pointer it up. The thing I was kind of saying here, note the fringes at the edge of the dark grain are these fringes here. So 1, 2 fringes here, 1, 2, kind of 2 fringes here. So it's pretty uniform in that grain. This is a pretty small recrystallized grain actually, and we can tell that because we know it happened to it. Again, this is from the hypervelocity impact craters I was showing before, and you kind of see these kind of ringy patterny. This is dynamic recrystallization, DRX as it's sometimes abbreviated as. Diffraction / lattice defects. Anytime you see contrast here, and we've talked about the formation of microbands, we know they're yeah, stumbling over my words. We know they're a dislocation structure. And so dislocation structures and are pretty much a lattice defect if you think about it. And dislocations, of course, are extra and missing row of atoms depending on your point of view. We have them all kind of grouping together to form this microband structure, and we see it reflected on the diffraction pattern here. So this is an example of diffraction contrast. I think now would be a good time to go into an explanation on electron diffraction. So we'll go into how electron diffraction occurs. Alrighty, so we're going to talk a little bit about electron diffraction. Hopefully you can read my writing. We're going to look at a one-dimensional lattice, and so a little bit different than lattice structures that we've perhaps seen before, but this is just to explain the concept. We have our atoms in our lattice, expertly shaded, and kind of going into this X direction. They're separated by our lattice parameter A, which is kind of a common concept. Diffraction if you think about electron diffraction, it's basically a reflection process. You think about it. And we can kind of take a look at some electrons traveling through this 1D lattice. So since we're talking about a reflection process of even the word diffraction itself, we're talking about the electron behaving as a wave. Now, this reflected wave is called the K vector. And we've seen this before, and it has its own wave function defined by psi sub k. Okay, so we're dealing with K space. We're dealing with some kind of abstract constructs, which we kind of come across repeatedly when we talk about electron diffraction. So let me kind of rewrite this in terms of A and A prime. And so we'll do A, B, C. And then we have some situations where the wave will kind of keep going, and then we'll have a situation where the wave will bounce back. So we'll have a spot where, let me just kind of draw, hopefully it doesn't be too confusing. We'll have a point where at A prime, B prime, and C prime, we have a spot where it went back. I should have made these red, I'm sorry. And if you've ever seen me derive Bragg's law, I go through several derivations of Bragg's law, and which is n lambda equals 2d sine theta, or lambda equals sine theta. And you watch me struggle with my camera. Hopefully this doesn't become too annoying to you all. We always talk about path difference, okay? And so when we have these reflections, we're getting constructive interference. And when there's, so we'll just say reflections. So we have a reflected wave, and then we have a pass-through wave, basically, okay? And this is, we can call this C, and it's a reflected wave. There's another wave that we'll have, which is S, and it's the standing wave. Just kind of passes through. And this is destructive interference. So kind of went off the paper there, destructive interference. So this, and I should have done this. This bounce back wave now has a path difference. And we always say the path difference is n lambda. Okay, so the path difference is n lambda. The actual distance it's traveled, so if you remember, this distance here between one atom and the other atom is the atomic spacing, or lattice parameter A. So this bounce back wave, it's gone from here to here, bounced back. So this bounce back wave has traveled to A. All right, so this path difference is really the difference it's bounced back. So it's actually traveled to A. So we can equate this path difference n lambda to 2A. N lambda equals 2A. And the big deal here is for constructive interference. Okay, so this is kind of an equation of a familiar form. Now, we've seen this before where we have an equation for lambda, and we can put this in terms of k. And we've seen this before talking about other stuff. So we can rewrite our equation 2a equals n 2 pi over k. K, we've also seen equals itself. K equals n pi over a. And we saw this when we talked about Schrodinger's equation and the electron dispersive function. And again, I'm very sorry this is so blurry. I will include it anyway, but then I need to put a better cartoon for you all to see. This is pi. I adjusted my camera a little bit, so hopefully this isn't so horrible. And again, I do apologize for the poor kind of video quality when I do this stuff on paper, but I deal with what I have. If you have any questions, always reach out. And anyway, let's kind of try to move on. Again, I'm sorry this is not the best. And if we remember, so this is k n pi over a. I'll try to make it look more like pi so you can see it. K equals n pi over a.
where n equals 1, 2, 3. We've seen this before in terms of energy levels and that kind of thing. We know that the kinetic energy equals to h bar k squared over 2m e. This is mass of the electron. So we've kind of seen this before. That's where some of this stuff was kind of seen. And we had n in there somewhere when we talked about ground state and that kind of thing. So kind of moving on just a little bit. All right, so we're, excuse me, situate here, bad camera. Okay, we're familiar with Bragg's law. That's n lambda equals 2d sine theta. We know from what we worked out before, two things we know. So we know that lambda equals 2 pi over k, so we got that. We're dealing with a one-dimensional lattice, so d in this case is equal to a. Almost kind of gave the punchline away. So we can rewrite Bragg's law and we can flip it over. So we can say that 2a sine theta is equal to, I'm flipping this around and then I'm substituting 2 pi over k for lambda. So n 2 pi over k. So we can kind of get to a new form of Bragg's law. The 2's will cancel, and then we can switch k for a and rewrite k sine theta equals n pi over a, and a is the lattice parameter, k is the k vector. This is kind of an important equation. It's a kind of an integerized, so we can call it k space Bragg's law. It's an integerized Bragg's law. So again, n equals 1, 2, 3, etc. So it's an integer. We know that we had electron energy because we talked about the kinetic energy of the electron before, and we basically said that Ke equals to h bar k squared over 2 times the mass of the electron. Okay, so we're going to be talking about energy, and we can just say E versus K. So we can draw a graph of E versus K. And so this is K space. That's what we're talking about here. And we see that some interesting things happen. So we can draw it kind of quasi-Cartesian-like. And we can have negative pi over a, 2 pi over a negative on this side. On this side we have pi over a, and over here we have 2 pi over a. I'll draw the discontinuity on one side just for brevity, and then I'll kind of show you a better cartoon later. So we have continuity here, but right here at pi over a, okay, we have a discontinuity and another discontinuity at 2 pi over a. And these discontinuities are spots where electrons cannot exist, okay? And so we can kind of make this into an energy band diagram. these discontinuities, again, are spots where electrons cannot exist. And remember now, we're talking about electron diffraction. We're talking about electron diffraction in metals. And we can basically say that, yes, indeed, metals do have band gaps. And so these band gaps, these are band gaps. And the band gaps are where the diffraction condition is met. Okay, so the fact that we're having diffraction in metals means that metals do have band gaps. Now the story doesn't necessarily end there, and we're going to talk about things in terms of 2 dimensions. The first thing I want to talk about is the spots where electrons can exist are called Brillouin zones. Brillouin zones. I hope I spelled it wrong or right. Hope I spelled it right, not wrong. Brillouin zones, and it's basically places where electrons can be. And so here, I should have drawn it more symmetric, but basically, I only drew it on one side. I'm sorry, but I'll show you a better cartoon. The first Brillouin zone is from negative pi over a to a. It's from negative pi over a to a. Negative pi over a to positive pi over a, excuse me. And then the second Brillouin zone is divided up into two spots, as you may have guessed, because there's a discontinuity here and another discontinuity here. So there's 2 other Brillouin zones. So there's the second Brillouin zone is either positive or negative. And so there's 2 of them. So pi over a to 2 pi over a, and on the negative Cartesian coordinate, negative pi over a to negative 2 pi over a. So first and second Brillouin zones. And again, the Brillouin zones are places where the electrons can be. At pi over a and at 2 pi over a on either side of our little graph here, we have spots where electrons can exist, and those are essentially band gaps, and they're band gaps in metals. And let's kind of lead into kind of the next kind of magic that kind of happens here in metals. And I'm going to kind of draw a 2D Miller indice this time. Let's see if I can do it well. Oops, I did it wrong. I'll make it real small since I skipped. Probably too small for my poor camera. Drawing dots, very cathartic. Hopefully you don't hear the singing in the background. All right, so this dimension here on this side, this is A, so we have A, and then we have this dimension here, and we've seen this before. We see this before talking about lattice structures. This distance is going to be A over square root of 2. Okay, so we have kind of 2 distances. So we have this kind of vertical horizontal distance. I'll draw it again here. A. So we have vertical horizontal distance A, then we have this diagonal, which is A over the square root of 2. And if we look at 2D Miller indices, and we're all familiar with Miller indices. We have 1, 1, 1, 1, 0, 0, 1, 1, 0, that kind of thing. We're dealing with 2D Miller indices right now, and it is 1 and 0. We have 0 and 1 are what we care about, and then we have one other one, which would be the equivalent of 1, 1, 1 in 3D, 1, 1. And it's kind of interesting. So we have different k vectors. We have different diffraction vectors associated with these Miller indices. So each has own diffraction condition. And we see this in the XRD all the time in 3 dimensions, right? So we know where peaks lie. 111 is generally an early peak on the spectra. So kind of try to imagine that. So we have different k vectors associated with each one. So we can denote this guy, k vector 1, and this one will be for 1, 0. And this is the Diffrax when k is plus or minus n pi over a, okay? K2 is 0 and 1. This diffracts when k is equal to plus or minus n pi over a, which makes sense because 1, 0 and 0, 1 are these two guys, okay? 1, 1, notice it looks almost, it's angular, so it's triangular, so it's very similar to the 1, 1, 1 plane that we see in 3-dimensional space, okay? So it's going to have different diffraction conditions. So these guys are going to have similar diffraction conditions because they're simply the inverse of one another. They're the same family, I guess you can say. This guy's going to be a different one, 1, 1. So K3, 1, 1, this diffracts when k is plus or minus n pi a over square root of 2. Okay, so it's going to have a different diffraction condition. Okay, so this is very important now. So now we have a case in these materials where we're having different diffraction conditions. Okay, we're looking at it in 2D just because it's a little bit simpler to explain it this way. But let's kind of take a look. So K1 and K2 are the same, and let's take a kind of a truncated look at this E versus K space graph. So we have n pi over alpha. We'll just do 1. N pi over alpha equals 1. And or n equals 1. My brain's getting away from me. And we can kind of draw, I'm drawing it not really how it looks, but that's okay. And, oh look, okay. We have a band gap. I'm going to try to draw, here, I'll draw it below it. I can mess up a little bit. Let's draw K3. And the thing that we want to kind of note now is that we can rearrange this guy. So this is square root of 2 pi over a. Okay, so it's a bigger value. Okay, so we actually have more space where the electrons can apply. Okay, so your Brillouin zone is actually bigger in this K3, right? So instead of going from negative pi over a to pi over a, we're going from negative square root of 2 times pi over a to negative square root of 2 times pi over a, so it's slightly bigger. Okay, so this Brillouin zone is actually a bigger zone, so this means that this gap is smaller. And so I'll try to draw it smaller. No, I didn't draw it smaller, so hold on, there we go. Okay, so the Brillouin zone is bigger, so the gap is smaller. So bigger Brillouin zone, we'll call it BZ. So what's kind of interesting is now there's a lot of electrons flowing around in metals, metals have a band gap, but metals conduct, they don't semiconduct. And the reason why they can conduct is we've talked about electrons, they keep going, then they change direction. Okay, so here, if you imagine the electron flowing through a lattice, the electron is going to change direction, and it's going to encounter a space with a smaller band gap. What we also find is that the band gaps overlap. Okay, so they have basically no net band gap. So let's just say this band gap down here, and I'm kind of drawing it, is the K3, and this band gap here is the, how many did I put? I put kind of 2. The K1. And I'll show a better cartoon after this. So the K3 and actually, yeah, this is the K3, this is the K1. K1 directions basically overlap. So the electron's going to go through, it's going to hit this band gap, but the electron's going to inevitably change direction because it'll hit a phonon or something, bounce around and go somewhere else. It's going to come to another place where this band gap is overlapped with this band gap, so it has no net band gaps, okay? Our net band gap of 0. So net band gap of 0. Hopefully you can read my poor writing of.
All right, so I made kind of a single slide to explain electron diffraction, and it's a little bit better than the preceding sequence of recording. And so that recording was done on older gear, kind of for another class, but I think it hopefully provides some in-depth, but I don't really think the quality is that good. So let me try to get my laser pointer. There we go. All right, so kind of recapping what was in the last video with a little bit less detail. You have kind of this row of atoms, and it's not a three-dimensional lattice. I guess it's kind of a one-dimensional lattice if you think about it. And so these atoms are separated by distance a, so this is analogous to interplanar spacing. So you have your electron coming, right? And your electron is coming in the form of the k vector, so we're talking about in terms of k space again. We've seen this in terms of reciprocal space, and I don't have my little squiggly line here, but k in terms of a wave vector, and I know early on in this class we said k equals 1 over lambda. When we kind of talk about it as a wave vector now, the wave has periodicity, okay? And so we add in this 2 pi, so k equals 2 pi over lambda in this description, okay? So it's a little bit different than what we talked about before. I'm just kind of putting it out there to show that there's different flavors of Bragg's law. That's what we're going to get to. And I already kind of showed the punchline. I meant to kind of animate it, but that's okay. So we have our wave coming through. 2 things are going to happen. It's either going to bounce back, so it's going to go from here to here, bounce back, or it's going to go on. And so where I have this little asterisk is a bounce back event, where it goes on with this not asterisk event. So when the wave hits an atom and bounces back, it's constructive interference. So that's where you're going to get diffraction. So when it's reflecting, that's where we kind of use these terminologies, reflecting, bouncing back kind of thing. The path difference between this bounced back electron, if you will, and the electron that passed through is some integer of the wavelength. And so Bragg's law language, we say there's a path difference that's related to some integral of the wavelength. We're seeing that again. There's actually a distance now that we have. So this bounce back wave has actually traveled 2a. So it's going to go here, bounce back, and go all the way back. So now it's 2a. Again, k vector is 2 pi over lambda. We can rearrange that and say lambda equals 2 pi over k. We know our path difference n lambda is now equal to 2a. If we look at Bragg's law, we can say n lambda equals 2d sine theta, so we already know that. So we can rewrite Bragg's law in terms of what we have up here. Since we're not dealing with a 3-dimensional lattice, we're dealing with only a 1-dimensional lattice. D is equal to a. So 2a sine theta equals n 2 pi over k. Okay, so we've integerized some of this stuff. Okay, so we rearranged it. Anywho, k sine theta now equals n pi over a. Okay, so this is another form of Bragg's law. And so kind of combine this with the maybe lower quality description I've given you, and hopefully it becomes clear. Again, if you have any questions, let me know. Thank you. All right, so you've seen how electron diffraction occurs kind of from a solid state point of view. We have kind of another solution for Bragg's law, and hopefully that helps kind of make some sense, and it's kind of cool that we get another flavor of Bragg's law, not just lambda equals 2d sine theta. The next thing we kind of want to talk about now is, so we know things diffract. We've seen this before, and with XRD, particularly in the XRD lab assignment you all had. And so we have allowed forbidden reflections. So allowed reflections come about as a result of constructive interference. Forbidden reflections come about as basically destructive interference. Okay, so that's kind of a high level, almost hand wavy explanation of it. But allowed reflections must satisfy Bragg's law, and I'm 99.99% sure all of you in the class have seen this table now. What I'm doing now is putting it in the context of electron diffraction. So this is an electron diffraction pattern of vanadium, which of course is BCC. And I want to point something out to you here, and let me kind of do some in situ editing. All right, did some in situ editing because I want to make sure that you guys see this. And so vanadium BCC, this is an electron diffraction pattern. It's quite old. It's a picture of a giant picture that I took a long time ago, actually. And I want you to note this fine ring here. So you notice all the other rings have spots, and here there's a spot with no ring at all. And so we have this first reflection, which is probably 110. Okay, I can 99.99% tell you it's 110. We have this second reflection here that is 200. But then we have this third reflection, but it has no spots. Okay, so it has no spots, but we still see something trying to sneak through. So it's a forbidden reflection. And according to this table, we're going to assume that it's 210 trying to sneak through. And so we're actually seeing a forbidden reflection on a diffraction pattern, which is kind of cool. So we're not actually seeing diffraction, but we're seeing where diffraction would occur. Were it not a forbidden reflection, there's just enough signal that we see this kind of ring, and that's actually really kind of neat. So we see the destructive interference of this electron beam / material interaction here. So I thought that was kind of cool. All right, so we've seen diffraction contrast, and here's kind of another depiction of diffraction / lattice contrast. And so here we're seeing dislocations, and they appear dark. And what happens is the presence of the dislocations causes the electron beam to go somewhere else, basically. And that's another example of a diffraction contrast. And so I'm not showing the diffraction pattern here because they didn't show it in their article either, I don't believe. But the contrast mechanism, again, this is diffraction contrast. There's some sort of defect in the material kind of showing up as black. And again, we're interpreting these micrographs by looking at the differences between black and white. I mean, the power of contrast is extremely huge. And we're also even seeing some other faults here in this material. And so this depiction kind of hopefully makes it a little more understandable. The beam passes through where you have a defect, and this is even showing a dislocation where you have some lattice distortion due to the presence of a fault or a dislocation. The beam is deflected, so it's diffracted really, and so it goes somewhere else. So it doesn't go to the imaging plane. So everything appears dark in the presence of these. We'll just refer to everything globally as a defect, as defects. So the defects appear dark because the beam is being deflected somewhere else. It doesn't have to be a defect either. So if you remember back to X-ray diffraction, we showed that if your material, if your specimen isn't oriented to the proper diffraction condition, you're not going to see peaks. Well, here, this is kind of the same thing. So we have different grains that are oriented in a drastically different way, and that's causing the beam to deflect somewhere else. Okay, so we have these lighter grains and they're oriented just so the beam can pass through them. And it's different than thickness contrast, and we'll get to that in a little bit. The beam is deflected elsewhere. We know it's polycrystalline. We know that we're getting some sort of signal because we're seeing this beautiful diffraction pattern. So this is diffraction-related contrast. If I were to go over to one of these other spots and image off of that, the contrast would reverse, basically. So this would be a dark field image versus a bright field image. And we'll see another depiction of bright field and dark field in a bit. Bend contours. So if your specimen is bent, has a wrinkle in it, if you will, you'll see some diffraction. This is my painstakingly drawn PowerPoint depiction of bend contours. It's kind of true to life. Okay, they're not very well defined, and that's how you can kind of tell the difference between a bend contour and a mass thickness contour. And here's an example. It almost looks like a shadow. They're not very well defined contours. And this is another kind of depiction. So you have your specimen bent, so there's lattice distortion actually because your specimen's bent, so the beam's deflecting elsewhere. The resultant image doesn't have very good definition where these contours are forming. So that's a bend contour. The next subject we'll talk about is extinction distance. And extinction distance will allow you, or the concept of extinction distance really allows you to figure out the thickness of your specimen. And the way I like to make an analogy for extinction distance is you're driving down a dark highway and your headlights are on, and you can kind of see where the beam of light coming off your headlights ends. And that depends on, the air conditions, how much humidity is in the air that night, if there's dust or something in the air. And that is my analogy for extinction distance. And so different materials have different extinction distances. Different orientations will have a different extinction distance, and it also depends on your accelerating voltage. And there are some tables, and I'll post the tables on Blackboard that help with doing extinction distance problems. And we're going to work this one out right now with copper. So we're using an older TEM, so 200 kilovolt potential, and we're assuming that our specimen's oriented 111 zone axis, and we'll get to zone axis a little bit later, but it's oriented in the 111 direction is what this really means. And there's this equation, very simple equation, and let me bring up the pointer. It's thickness T, N is the number of fringes, and this Greek letter, I think it's eta, is basically the extinction distance for a given condition, and it's on a table. And I'll post that table on Blackboard. We'll see it worked out very shortly, and then you'll have hopefully a better understanding of how we use extinction distance. And again, different for different materials, accelerating voltages, and orientations. All right, so we're taking a look at this problem here. I think I may have actually skewed the image a little bit. The diffraction pattern looks a little funny. But that's okay for the purposes of this exercise. So we want to know the thickness of this specimen. And it's very, very important to specify where you do some of this stuff. And so I'm going to look in this region here because I'm not quite sure about this region here. This region here, I definitely see 2 fringes. And so I'm going to use those 2 fringes, and I also see 2 fringes here on the other side, and I'm 99.99% sure that there's 2 fringes here. Here I'm not quite sure. I could debate, maybe this is 1 fringe and maybe this kind of counts as another fringe, but I'm not too sure about that. But this one to me is more definite. So if you're doing this kind of stuff, sometimes it helps to say where you're making the measurement. So if you're writing a paper or something, you can alter your micrograph with much better than I have done with my hand drawing. You can use a shape or something in PowerPoint or some other graphical software. So we have some information. So we're 111 orientation here. So we're oriented in the 111 direction. We're going to use this equation here. Thickness equals the number of fringes times, I believe this is eta. And that's really just extinction distance. And we also know that it's copper. And copper is a FCC. And some other elements, of course, can be different in terms of their phase. And if you're looking at a 2-phase titanium alloy, for example, which you have alpha and beta, there's BCC and hexagonal close packed, excuse me. And they would have different extinction distances depending on the phases. So you kind of want to know what you're looking at. But right now, again, kind of a reminder, I'm going to use this region here, has 2 fringes, and we have other bits of information. We have 200 kilovolts, and we know it's a 111 orientation. And man, it's a little kind of make things consistent. So we're in it 111, and what we have here, and I'll post this table on Blackboard if I haven't already, is table of dynamic extinction distances, and it tells you it's in angstroms, so we're going to get units out of this. This is for some FCC materials, and I have tables for other materials as well, and I need to kind of look for them. But again, it's this nice epsilon symbol. So it's the extinction distance in angstroms. When we plug our information in to this simple equation, we're going to end up with angstroms as our units. So that makes some sense because we're looking for thickness. And I love how it's just generic stainless steel. That's lovely. So we have aluminum. I believe this is gamma iron, Inconel, straight up nickel, and copper. So here's copper. Here's what we want. And this is the accelerating voltage, so 200 kilovolts, and I know that because accelerating potential in kilovolts. I'm kind of making a big deal out of reading off of a table, and maybe I shouldn't. But anyway, 111 is the first column here. Oops, excuse me. 111 is the first column here, and so I get, oh, come on now. Watching me struggle with my tablet. 306. Let me use the highlighter. I get 306. So here, let me zoom in. So T equals N, which is 2. We counted 2 fringes over here, times 306 angstroms. And T equals 612 angstroms. Very thin specimen. So again, hopefully this is helpful. It's basically just reading off a table and plugging and chugging. So 306, just double checking I did it right, 111 orientation, and we're good to go. So hopefully this is informative to you and helps you in your future TEM endeavors. Bright filled and dark filled. So back here, we've seen, passing through bright. It looks dark where it's dark, but it'll make a beam on the diffraction pattern space, if you will, diffraction pattern plane. So you can image off of that diffraction pattern plane. So the bright field uses a transmitted beam to form the image. The dark field uses a diffracted beam to form the image. What I have, this was off Instagram. This is a really nice image, actually. And I found it quite recently on Instagram. It's another depiction of dislocation arrays. They have a slightly different geometry. They're on grain boundaries. I don't remember the material. I'm going to guess it's aluminum because there's these pretty large precipitates. I'm just guessing. And it's from these guys, this organization puts up a lot of nice stuff. But this is bright field. This is actually dark field, and this is high angle annular dark field. And this terminology is actually more used for STEM. And so standing transmission electron microscopy. So we're not going to see a diffraction pattern here because the beam is rastering. So it's a mode that we see on some SEMs, and also some TEMs can have STEM mode as well. And I should probably talk a little bit more about that at a later date. But you still have a bright field image and a dark field image even on STEM because the signal goes somewhere else. And if you look, dark field is pretty much the inverse of bright field. And so all the electrons that were deflected by your defect in some way go to the dark field plane. You have to use either an aperture, or perhaps you have a detector that's, if it's a diode based system, that lives on the dark field plane, and you can image in dark field basically. So if you notice, it's the inverse. Very beautiful. These are dislocations all along the grain boundaries basically here. It's really kind of neat. This is kind of cool here. I always love looking at this stuff. It's really interesting how there's always a sense of order to how this stuff kind of comes together. Looking at the aperture systems, this is for TEMs. This is out of the Brandon and Kaplan book. You put in your selected area, you put in your selected area aperture here. So this is the dark field setup, and this is the bright field setup. And I don't necessarily like this schematic. I'll show you one I like somewhat better from Hitachi. But the diffracted beam is living elsewhere. You can only see it if you're putting in an aperture. And this schematic doesn't allow me to understand it all that well, you know, and you take out the objective aperture according to this one, and you put in a selected area aperture, or you use a larger objective aperture to see diffraction patterns, and then you see your spots. I like this depiction a little bit better than the Brandon and Kaplan image. This one came from Hitachi, and so you have your specimen. This is showing that your diffracted beam is going somewhere else, and you move your aperture basically. And this is almost a little incorrect because you have to put in a selected area aperture to see the diffraction pattern. So I'm bothered a little bit that I can't find a good schematic to show you all how this actually works. But this is, in my brain, a little bit more correct. If you combine the two schematics, I hate to tell you this, but if you combine the two schematics into one schematic, it's more like real life. So here, this is showing that imagine you have a diffraction spot off the axis of your transmitted beam. You move your aperture so you're creating the image off of that diffraction spot. So let's go up here and find a diffraction pattern. So that's not a very good diffraction pattern. Let's use this one because I already kind of talked about it. So the image here is created by this beam. We put in our aperture and we make our image off of this beam, okay? When we make our image off of this beam, we get basically a dark field image, okay, because we're making the image off the diffracted beam. And that's more like this. So you're making your image, you've moved your aperture over to where the diffraction spot is, and then you're imaging off of that. That's aperturing to make a dark field image. You have to have a diffraction pattern in this instance to do it. For this high annular dark field image, the way a stem is made, there's usually a diode detector that has detectors where diffracted beams are going to hit. So it's a little bit different. I should probably find a schematic for that. In a TEM, it's totally aperture controlled. You put it in aperture so you can image off of a diffracted spot. That's how you get your dark field image. All right, so this seems like a good place to stop. We'll pick up a little bit more on diffraction patterns and indexing diffraction patterns in the next lecture. Hopefully you have a bit more understanding of sources of contrast, and I hope this has been informative to you. So thank you all for your time.
Oh my.
It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.